Hello students, so welcome you all to the lecture number 2 of our series oscillation. I hope you have seen the lecture number 1 about simple harmonic motion. So in second lecture we'll discuss about damped oscillation, or you can say damped harmonic vibration. So before going to damped harmonic vibration, we'll start or we'll discuss about what is free vibration first. Free vibration is what? When from the name you can identify it is free. That means there is no resistive medium, there is no opposing medium. So when the body vibrates in the absence of some retarding medium like air resistance, friction, because these are the opposing force which will decrease the energy, which will decrease the amplitude. So when these mediums are absent, the vibration is said to be free. So we will start from that. So here you can see it is written about free vibration. The vibration which takes place in the absence of some retarding medium like air resistance, friction is said to be free vibration. It's said to be free vibration. Clear? So since the body is free to move, whatever the frequency it has, that is said to be the natural frequency of the body. Natural frequency, you can see it is written natural frequency of the body. So without any retarding medium it is vibrating, so the frequency remains same, as well as the energy and the amplitude. So amplitude already we discussed in the last video. The maximum displacement from either side of the mean position is said to be amplitude. So here, since it is free to move, it is moving in the absence of any retarding force or retarding medium. So its energy as well as the amplitude remains constant. So in free vibration, energy of the body, which has to be the total energy, and the amplitude of the vibrating body always remains constant. So if you plot the graph, then the graph will be like this. If you plot the displacement graph, displacement, already we have mentioned displacement y equal to r sin omega t we have derived in the last class. So here omega t angle, or you can only write down t also. Then here you can observe that there is no decrease in the amplitude. This is in case of free vibration. This is the amplitude. So amplitude will be remains constant. Similarly, if we plot the energy, total energy, if we plot energy along y-axis and time along x-axis, in both cases you can see as the amplitude constant, the total energy will be constant in free vibration. So free vibration, both amplitude and energy constant. Then we will go to the damped vibration. Free is also said to be undamped. Free is also known as undamped vibration. So from the name you can identify now what is damped. Free is in the absence of any retarding medium, but when the body vibrates in the presence of some retarding medium, that is said to be damped vibration. So retarding medium, that means already we discussed like air resistance, friction. If retarding mediums are there, then there will be decrease in amplitude, there will be decrease in energy. In damped case, always you can observe there will be decrease in amplitude as well as the energy. Best example you can see the simple pendulum. If we move the simple pendulum from one point, then leave, then it will vibrate or it will oscillate, but it will not return back to the position it achieved in the previous vibration. In the first vibration, if it moves to 10 centimeter from mean position of rest, in second vibration, due to the presence of air resistance, there will be a slightly decrease. The distance traveled will be less than that of 10. So here, in both cases, if we see energy case as well as the amplitude case, there will be a decrease. If we plot the energy, you can see there will be a drastic change in energy. Here the maximum, then it is exponentially decreases with respect to time. Similarly, if we say the amplitude case, amplitude also gradually decreases with respect to time. Time or omega t, whatever you can take along x-axis. See here the amplitude up to this much. As time proceeds, the amplitude gradually decreases. So this is the difference between a damped oscillation and undamped oscillation. Undamped means free, where the body vibrates in the absence of any retarding medium. Damped means when the body vibrates in the presence of some retarding medium. In undamped case or free vibration, the total energy always remains constant, but here energy exponentially decreases with time. In undamped case, the amplitude remains constant. In damped vibration, the amplitude gradually decreases with time. So next, we will derive the wave equation of damped oscillation. So in order to derive the wave equation of damped oscillation, we have to find out what are the forces involved here. Once we find the forces, then you can rearrange to find out the damped equation. So the different forces are, one is the restoring force. Restoring force. Restoring force is responsible to bring back the body to its mean position, and it always depends upon the displacement, but both in opposite direction. Already we have derived in the last video. So F is proportional to y. There is a negative sign, that means both are opposite. So F equal to minus ky. This is one force. Fr we can write down in order to identify restoring. Another one is damping force. Let FD. So damping force means the force which is responsible to decrease in energy as well as decrease in the amplitude. So just like air resistance, friction, any type of opposing force will be there, and this type of force depends upon the velocity of the body, and since it decreases the energy as well as the amplitude, it is always in opposite direction. So damping force is equal to some constant V, damping constant you can say. Then instead of V, we can also write down minus B dy by dt. dy by dt, rate of change of displacement, because here we have expressed in terms of displacement. Then another type of force is that which is said to be the inertial force. Inertial force means already we know that F equal to ma, or we can write down F equal to m d square y by dt square. So these three forces are involved in vibration of a damped motion or damped oscillation. So what happens in equilibrium? Resultant force or the inertial force is balanced by the opposing force. So this is equal to the restoring force plus the damping force. So we have the formula here. We have the formula here. We have to just use it here. So force equal to m d square y by dt square equal to, this is minus ky and this is minus b dy by dt. So this is the equation we get. Then we will rearrange it and modify in order to find out the final differential equation. See here. So when we have m d square y by dt square equal to minus ky minus b dy by dt, we can divide m on each term. So this will be d square y by dt square plus, if we take to left hand side, this will be b by m dy by dt, because here it is negative. If we take to the left hand side, this will be positive. Again, this is negative. If we take to the left hand side positive, this will be k by m y equal to 0. Now for convenience, we have to use the values of b by m and k by m. B by m equal to 2r and k by m equal to omega naught square. In simple harmonic case, we have written k by m equal to omega square, but here we have written omega naught square. This is just a differentiate between omega naught and another omega will be there in the derivation. I will explain what. Okay, so omega naught is nothing but the natural frequency of the body, and whatever the omega, whenever we will write omega, that will be the resultant frequency or said to be the damping frequency, and 2r is the damping constant. And always remember, 2r is written here just for easy mathematical calculation, just like you remember electric dipole. In electric dipole, we have mentioned the distance as 2l, 2r, 2x, like that, because in calculation we need half of the distance. So it will be like r, then square will be r square, then half of that square or a cube of that half value will be r cube. But if we have written as r, then it will be r by 2 square. that means r square by 4 and so on. So there will be a complication in the calculation method or mathematical process. So for easy calculation itself, it is just written like 2r. So now the equation will be d square y by dt square plus 2r dy by dt plus omega naught square y equal to 0. This is the resultant differential equation of the damped harmonic equation. Here in mathematics you must have studied about the degree as well as the order. So order means the highest order differentiation. So it is a second order. Here you can see double derivative is there. So it is a second order equation, and degree is nothing but the power of the highest order term. So second order and degree is 1 is said to be linear, and all the terms are function of y, and on right hand side is 0, so it is homogeneous. So this equation, which represent the wave equation or the differential equation of damped oscillation, is a second order linear homogeneous differential equation. If equations are like this, then their generalized solutions are in the form of y equal to a naught e to the power minus rt sine omega t plus phi, plus or minus phi, or here also you can write cos, because harmonic functions can be represented in terms of trigonometry like sine or cos. So the difference here you can see, here we have omega naught, but here I have written omega. This is a generalized solution where a naught is a constant, and here you can see r is there. If we have written r, this will be r by 2. So for easy calculation itself we have written 2r. Omega is here the damping frequency. So where the formula of omega is omega naught square minus r square, or we can write down omega naught square minus r. What we have written? B by m equal to 2r. So r will be b by 2m. We can write down b by 2m whole square. This is the damping frequency, and omega naught is the natural frequency of the body. Then we will analyze this damped equation of d square y by dt square plus 2r dy by dt plus omega naught square y equal to 0 of this part. So this is the damped equation we have. We have to find out the analysis method. So analysis method means just we have to find out a particular solution. So let assume the solution of this equation is like this: a e to the power alpha t. We don't know what is a, we don't know what is alpha. These are the unknown quantity. We have to find out these roots or this solution. So if we have y, we can easily calculate dy by dt. So this will be a alpha e to the power alpha t. Again double derivative we can calculate, d square y by dt square, which will be a, then again another alpha will be there, so alpha square e to the power alpha t. If we assume this is the solution, then this must satisfy the equation. So we have to use the values of y, dy by dt, d square by dt square in this equation. So once we use there, then we will find out like this. So this will be the first value, this one. So a alpha square e to the power alpha t plus second one is 2r into dy by dt, 2r a e to the power alpha t. Alpha is there, plus last one is omega naught square into this. So omega naught square a e to the power alpha t equal to 0. Now we can take common a e to the power alpha t. A e to the power alpha t, if you take common, this will be alpha square plus 2r alpha plus omega naught square equal to 0. As this is our solution, assumed solution, this cannot be 0. So the term which is multiplied with this will be 0. So we get alpha square plus 2r alpha plus omega naught square equal to 0. From here we will find out the roots alpha. This is just a quadratic equation. So for quadratic equation, you must have remembered the formula minus b plus minus b square minus 4ac square root divided by 2a. This is the root. To calculate root, we have to use this formula. So in next page, we will calculate this. We have the solution alpha square plus 2r alpha plus omega naught square equal to 0. This is the equation. We have to find out the solution of this. So this is in the quadratic equation. So in quadratic equation, we have the formula like minus b plus minus b square minus 4ac. Directly I am writing here. So directly I am writing here. So this will be minus 2r plus or minus b square means 2r square minus 4ac, a is 1, c is omega naught square root divided by 2a, a is 1 here. So we can have the value like this, minus 2r plus or minus, here you can see this will be 4r square minus 4 omega naught square root divided by 2. And this is minus 2r plus or minus, we can take common. If we take 4 outside, this will be 2. So 2 times of square root of r square minus omega naught square divided by 2. Here you can see we can cancel 2. So this will be minus r plus or minus that square root term r square minus omega naught square. Here we can take 2 common. These 2 are there, we can take common. This will be minus r plus minus r square minus omega naught square root. So we have 2 roots. One is alpha 1. Let alpha 1 we have written minus r plus that square root term r square minus omega naught square. Another one is alpha 2, which is equal to minus r minus of that square root term r square minus omega naught square. So since we get 2 roots, we will have 2 solutions. One we can write y1, which is equal to a1 e to the power alpha 1. Another is y2, which is equal to a2 e to the power alpha 2 t. T will be there because we have considered the solution as a e to the power alpha t. Now the most general solution will be y equal to y1 plus y2. So y equal to, instead of y1 we can directly write on a1 e to the power alpha 1 t plus second one is a2 e to the power alpha 2 t. So this is the generalized solution of this differential equation. And here also you can do one thing, you can put the values of alpha 1 and alpha 2, where alpha 1 equal to minus r plus r square minus omega naught square root, and alpha 2 equal to minus r minus this square root term, which is equal to r square minus omega naught square. So this is the most general solution. And a1, a2 are always constants, whose value can be find out by using the different conditions value. Hope you understand this one. Okay, so here one more thing is there, the roots we get like alpha 1 or alpha 2, whatever you can write, or we can write both alpha 1 and alpha 2. Alpha 1 we have written minus r plus r square minus omega naught square. Similarly minus r minus r square minus omega naught square. So here omega naught is nothing but the natural frequency, and r is nothing but, we have written that constant b by m equal to 2r. So r will be b by 2m. So this is the damping constant. Due to the damping force, there will be decrease in energy as well as decrease in the amplitude. So accordingly, depending upon the relation between r and omega, it is of 3 different types. One is when r is less than omega naught. Second condition, r greater than omega naught. Third condition, when r equal to omega naught. When r is, damping constant is less than the natural frequency of the body, this is said to be underdamped condition. Underdamped condition. That means whatever the motion of simple pendulum you are observing, that is underdamped, in which the body is oscillating or vibrating. This is overdamped condition. This is overdamped condition where the opposing force is much more as compared to the natural frequency of the body. So this is overdamped, and this condition, when both are equal, this is to be critically damped. Critically damped. One is underdamped, second one is overdamped, third one is critically damped condition. So here again, if we plot the graph for displacement, so for damping case we know that this is with respect to t or omega t. Then I will explain which one is damping, under damping, and which one is over damping. Okay, now see, three different graphs are there. So this is for displacement with respect to time. This white color line is nothing but the damping, which is said to be the under damping. Then this one is said to be, the yellow color one is the over damping condition, and this is said to be the critically damping condition. And this white one is under damping condition. So here you can see, in case of over damping condition, the displacement. Similarly, you can see in case of over damping condition as critical damping condition, in both case the displacement decreases, but in critically damping case the displacement decreases more rapidly as compared to the over damped condition. So this is all about the damped oscillation. If you have any doubts, you can comment so that I can know what type of doubts you have. We can clear that one. So if you like the content, please do like, share and subscribe the YouTube channel for more such physics contents. Thank you.